Okay, so yeah, we can start. Get started. So okay. Um, all right. So let me recall what we did. One of the things we did last lecture. So we looked at loop expansion. So this is a recall. Looked at loop expansion. So then we look at log of the partition function normalized like this. Then saw that we can write it as sum over loops from no loops to infinity log z over z0. Okay, so it's like this, and it's better like this. And then the notation was J here. This is a notation, and this is H bar, the power of J minus 1, where this quantity log of Z over Z0 J is a sum over, well, there are some G factors depending on coupling constants and all this, but there is essentially this is the sum over connected graphs with J loops. You see? It's connected because we are looking at log, but then we noticed that the number of loops is a negative Euler characteristic plus 1. There was a relation, so we managed to change the Feynman's theorem to this form, and then a number of loops appears with that. So for j equal to 0, there are no loops, means that the 0 component is the summing over trees. We're summing over trees. And then the next term, we are summing over one loop things, so there's no h bar in that. And this is summing over one loop things, and so. All right, we also saw that in this regard, actually this three component of this, the 3 log z over z0, 0, this is negative s of x0. So the 3 part, you actually don't have to do any calculation. You just, well, you have to do some calculation. X0 is the critical point of S, where S prime of x0 is equal to 0. So basically, this is the classical solutions, equations of motion. This is x0. And this is a classical equation of motion. And then this is the classical action. So this is classic. Summing over trees is classic. And then the next part, the one loop component, which is log z over z0, right? One loops, it's a log det, logarithmic determinant is log of det b over det is double prime of x. You see, this is the Hessian matrix of the function at this critical point, and we are assuming that this is non-degenerate, so this is certainly invertible matrix, and we are dividing these two matrices and take determinant and then take log. So this is the one loop component. Where here S of x, of course, here it all came from a action which is the quadratic part to start with, and then negative sum GI. This part, I don't know, we can just write maybe BI of x over 5 factorial and x0. Well, I already said what x is a critical point. Creating point equation, which if you do it in the actual case, this gives you equations of motion. Equation of motion. Okay, so that's one of the things that we did in the last lecture, which I'm going to use it today. But there is also, it's also possible to extend, and in fact, it's crucial to extend Feynman's theorem to the case where you have these insertions. We need to have insertions, so some fields coming from outside. That's very important. So this is mild extension of Feynman theorem. So what is that? So imagine you want to compute the following quantity. So let so these correlations L1, L2, L cap n, that is by definition be equal to h bar, the power negative d over 2 exponential of s of c over h bar integral over rd, get rd L1x ln x exponential of minus s of x over h bar dx, right? But s is as before, is over there. It's what we have over there. These L1, Ln are linear functionals on Rn. So these are like, it picks up, for example, one component of the vector x, maybe xi1, xi2. But this is in general, we want to think of them as tensors of rank 1. These are tensors. Okay, so because they are covectors, elements of the dual vector space. That's what they are. And yeah, I mean, so in actual computation, it's important to compute these things as well. And in this case, actually, same proof as we did, you can carry it in this case, shows that this guy is actually L1, L2, this correlation to Ln is equal to, well, there is this 2 pi, this factor is always there, e over 2 over root determinant of b, and then the sum over gamma, let me write it like this, g n and capital N. So here I just write h bar to the power negative Euler characteristic of the graph gamma over order of orthomorphism of gamma symmetry factor times f gamma of L1 Ln. So the new ingredient here are these f gamma L1 Ln that we didn't have before, and also this space of graphs. So Gn, and remember n is a multi-index that's dictated by these coefficients that appear over there, right? So so basically, this is a set of isomorphism classes of graphs with n labeled external vertices, with n labeled external vertex or vertices, and an I-valent internal vertices, I-valent internal. So basically, what you do here, you fix these external things. 1, 2. Actually, you put L1 here, L2 here, L3, for example, and then L4. Imagine there are 4 external things. They're called insertions, for n equal to 4, for example, in this case. And then we look at all possible graphs that you can put inside, where these graphs satisfy the condition that we always have. They have an I-valent vertex. But these guys in the external are labeled. We are not allowed to permute them or anything. So they don't contribute to symmetry factors. And in fact, in the definition of symmetry, we have to make sure that they keep these external things intact. They don't change them. They change only internally. And yeah, and these are tensors. So the final rule is as before, except that now we have these 4 more or n more tensors that also we have to contract. So then, so final rule basically is decorate each gamma belonging to G and N with the tensors So we decorate, we put tensors Li on the external edges, on vertices, Li on external vertices. They are labeled, so we know where to put. Once for all, we fix one labeling, and that's it. And then Pi on each I-valent internal vertex. On each I-valent internal vertex. And then we contract, and then just and then contract. Then we contract. Okay. So that's what I mean, as I said, the proof is exactly like before. You just take this exponential, write it out, I mean, expand it, and then use Wick's theorem, and then you bring in this result, group theory result that we have. But we cannot permute these external ones because they are not needed to permute. They're already there, they're already down here. These are the ones that are coming down that have to be permuted. Okay. We also saw a result which was we proved the Khalkhali's theorem about labeled trees, number of labeled trees with n vertex. Now we're going to prove another result about trees, which is more specific. So let me tell you what we want to do. Any questions? Okay, so now, so next thing is counting trivalent label these with n equal to 2k, even number of vertices. First of all, I mean, this I have to say what I mean by trivalent, because not all vertices can be trivalent, because the tree has to end at some point, and then that vertex is going to be one-valent. So the external vertices are allowed to be one-valent, because otherwise we wouldn't have any trees like that, right? But the internal ones are trivalent. So I mean, an example of this is like this, for example. Okay, so this is one example. Yeah, that's a tree. Yeah, that's trivalent. By the way, something we have to note that there exists no trivalent tree or label. Of course, I mean we have to label them again. Okay, so 1, 2, 3, 4, 5, 6. And you can imagine that if I bring this 6 here, you're going to get another label tree, trivalent tree, and so on. So there are many. There exists no trivalent tree with odd number of vertices. You can prove that easily with odd number of vertices. Okay, so this is a common. So that's why we look at even number only. Okay. So to do this, we just look at an action. And the action, it's dictated by this here. It's trivalent. So you just take a quadratic action as usual, plus a cubic action, cubic term. And that term that we had for KV, where we had e to the x, because we did not specify the number of vertices. We allowed any number of vertices. And if you put e to the x, you're counting all of them. Is e to the x is some xn over n factorial. That's exactly what you want. So that's more or less clear that you have to choose that. I thought about it. But in this case, it's also a standard that we have to choose this now, this action. So s of x is equal to, you just pick it, s of x is equal to 1/2 x squared. Well, this is the quadratic part has to be there, minus g times x plus x cubed over 6, which is 3 factorial. And you can see why. This x corresponds to this external here, for example, vertices, degree 1, and x cubed correspond to these things. So this will generate only this type of trees if we look at the tree part of the expansion, which can be computed using equations of motion, as we'll see. Okay. So here I just write critical point equation. X0. I mean, we have to solve this equation. So it's going to be x minus g times 1 plus x2 over 2, right? equal to 0. So luckily, this is a quadratic equation, and x0 is equal to 1 minus root 1 minus 2g squared over g. Yeah. Okay. So the classical component or the three component of the action of the expansion is
sorry, Masoud, just maybe I'm missing something, but there are two roots for this quadratic.
Yeah.
Right. So what happens to the other two?
Right. Good question. There are two roots. Why did I take this one? Right. You see, usually, well, I guess the other root should be plus, right? What if I took that one? As g goes to 0, this blows up. So that's not a good route. That tells me that this is not a good choice. I have to choose something that as g equal to 0 is 0. Because I know that if g is equal to 0, then the critical point is just 0. So I discard that one. Yeah. Maybe it's not a very strong reason, but something has to do with this. That's a good question. Okay, yeah. All right, so then sometimes I'm writing log, sometimes I'm writing ln, but it's okay. Ln of z over z0. Which is sum over 3's. This is equal to negative s of x0. So we have to take this and substitute it into this equation of x to find the value of the action at critical point. So this is equal to 1 minus 2g squared to the power 3 over 2 over 3g squared minus 1. Right? And we can, so this is a function which is nice at g equal to 0. It's a regular function at g equal to 0 because you see, I mean, there is some nice cancellation. So then we get that this guy, and we can take the Taylor expansion of that guy, right? If you do the Taylor expansion using Newton's binomial theorem, actually, that gives us some n equal to 0 up to infinity, 1 times 3 times 2n minus 1 over n plus 1 factorial. Or could be 2 factorial, actually. Times g to the power 2n plus 2. Okay, so this sum has to be equal to this sum over 3's. This is the thing. So if we compare this with that, we get the theorem that this is exactly the number of, so the number of trivalent labeled, that's important because Yeah, there is this 2k factorial and then divided by order of automorphism that creates label all possible labelings on unlabeled. Because this is a sum over unlabeled trees, but the combinatorial coefficient, the symmetry factors, as like in the case of Khalkhali, gives us that this leads to the formula for labeled trees. So trivalent labeled trees with n equal to 2k, where this is 2k minus 3 double factorial, 2k minus, okay, 2k factorial divided by k plus 1 factorial. Right. I mean, for comparing this with that as before, we get this. I mean, it's very easy to see that, of course, this is an integer. So, but it's a number of trivalent trees and so on. Okay. Now here is there's an amazing idea, which is, I will start discussing now, but I don't think we can finish it today, but I'll still discuss. And that is, that this is it's an amazing idea. This is somehow, I don't know. I mean, in math, we usually don't think in terms of this. So this is another contribution, I think, purely by physicists to mathematics of these things, which is called the idea of effective action. What do we mean by this is the following. The idea of effective action is the following. Okay, so the idea is that, look, I mean, we had this, okay, uh, um, we have, I mean, the motivation is the following. So we have, of course, this is the third time today I'm writing this. Log of ZS. So this is the action. This is the partition function of that action divided by Z0. And if we want to compute the tree part of this expansion, so this is sum over trees. Of course, it's minus S of x0 according to what we have there. Minus S of x0. So now the idea, this amazing idea is the following. Can change, and that's very surprising actually, can change S to a new action infinite term you have to add to it usually, can change S to a new action, S effective, such that log of Z S effective, Z of S effective over Z0 0 is equal to the original connected partition function. Okay. Okay, so let's go slowly. Imagine you create a new action by somehow adding extra terms to your original action with s of x, call it s effective of x, such that your partition function, and we want to compute this, is actually the 0 component of this new action, partition function new action. But this we know we can compute by just this formula. We can just take the derivative of this, finding its roots and evaluate, and then you're done. Okay. So if you manage to construct this effective action, then you have solved your problem completely. The partition function is at your disposal. You have to solve this classical equations of function and then evaluate, and that's it. And that's what we want to do. So that's why we can say solving quantum field theory, solving QFT, i.e. a partition function, essentially is the same as finding effective action. Okay. Yeah. So in other words, basically classical theory for effective action becomes quantum theory for the original action. I mean, this is a mind-blowing idea if you think about it. Why such a thing should exist even? Don't know. I mean, that's quite ingenious, daring idea. And the thing is, this exists. There is a perturbative expansion of S effective in terms of S, and then corrections, which are governed by powers of H. I will explain next. I'll try to explain next. I'm not sure. Can completely explain it yet. So for this, we need the idea of okay, to define or to find rather less effective. We need one concept, which is one particle irreducible graphs. We need one particle irreducible graphs. So these are generically denoted by 1 pi graphs. 1 pi is always like this. 1 pi graphs. Okay. So what is a 1 pi graph? It's the following. There is a question in the chat. Sorry. Taking the other route works in the strong coupling limit, the non-perturbative sector. That's yeah. So you mean when G goes to infinity? Brett, you have to send me the details again.
Will do.
Okay, thank you. Yeah, I think what you say makes sense. So the other route is also important, but in the strong coupling limit, which is, yeah.
Cool.
Excellent. Yeah, thank you. Very good. So yeah, so let's now. Okay, so first of all, what is a by the way, can you see when I reach the margins the boundaries of the board? Is it? Yep. Yeah. Okay. Say yes. Okay. Thank you. Good. So I can use the whole board. That's great. Okay. So first of all, a bridge in a graph, it's an edge that if you cut it, it makes the graph disconnect. An edge E in the graph gamma, an edge E such that gamma take away E is disconnected. Okay. And one PI graphs these are graphs without any breach, with no breach. These are graphs. Of course, we want them to be connected. Graphs with no breach. I mean, this graph, for example, as you can see, is not one PI. I mean, this is a breach. If you plot it, this is not a breach. These are not. And well, of course, obviously, I mean, something like this. It's a two-valent connected graph. It is one PI. It has no bridges. If you cut any of these edges, it still is connected. You cannot disconnect by cutting.
In the first example, why is the external edge not a bridge?
Oh, the external edges, we don't consider them. They're okay. Yeah, we don't touch them. We just internal edge. Yeah, because you can always cut it and then you get some vertex disconnected from the rest of the graph, and that's kind of okay. We don't want to touch them. Okay, so then the notation is that let G of one PI and N, capital N, that's isomorphism classes, iso classes of one PI, one particle reducible graphs with an I-valent internal vertex and n labeled external vertex. And let me go. External vertex. Then there is a formula for this effective action in terms of summing over such graphs. Now, the formula is very similar to Feynman's recipe for partition function, but this one now is the recipe for effective action. So here's the formula, which is really remarkable. Okay. So here is the the effective action S F is given by SF of X is equal to BXX. The quadratic term doesn't change, same, and then sum bi tilde over I factorial I bigger than equal to 0, where this b tilde, this function, where b tilde, yeah, so this whole thing we call it b tilde. So I just write one formula for all of them. So b tilde xxx is equal to sum over all multi-indices n, as in Feynman's theorem, by ji to the ni. Sorry. And then sum gamma belonging to G 1 pi n. Then we do h bar to the power negative Euler characteristic of the graph plus 1 over order of automorphism of such graphs. And then, yeah, okay, so again, here's a different kind of Feynman rule we have to be careful. So we put x star, where x star, yeah, where x star is a tensor, is a covector from Rn to R. You see what you want to do? You want to evaluate this p tilde on some xxx, right? So that's a number, that's vector in Rn, multiple. For each such vector, you define a linear functional x lower star is a corresponding covector from Rn to R is defined by x star of y is just inner product of x and y. Oh no, it's just p of x. P of x. Yeah. Yeah, it's this one. Okay, and then yeah, so then what you do again, so we put here x stars. These are external labeled vertices, one valent always. And then internally we put these BIs. And that's the Feynman for this. So basically, as effective is can be expanded like this: S plus H bar S1 plus H bar squared S2. Yeah. Okay. So the proof of this is not difficult, actually. Just guessing what to do is certainly, difficult. It was difficult, but I mean, coming across the idea. But the proof is not difficult. I won't give the proof now. I will give the proof later on because I want to give some examples so that makes the proof kind of more natural. But again, it needs a little bit of some work on graphs, so that's not so bad. And also, so proof uses this expanded version of Feynman theorem I wrote at the beginning. Uses Feynman 2. Let's call that result Feynman 2. So I mean, this comes later. But the important thing is that such a thing exists. Always. I mean, it looks like that. So what? I mean, computing this looks like is same amount of work as even more. It looks like than the original problem. But in reality, you only want to compute here. I mean, this is of course known only S1. Hardly you want to go to H power 2. If you do here, then you are pretty good. And to compute it here, all you need to do is to do Legendre transform, and that's the thing I want to discuss. So using Legendre transform, actually computing S1 is quite straightforward, and then we'll get to. And that's all we care. All right. So now let's okay, let me see if there is a question still. Oh, okay, no, there was a comment. That's okay. Okay. So there is something called Legendre transform, which is a beautiful idea. So I will just explain it, and then you should see what's going on. Legendre transform. And the one are graphs and effective action. Right. Okay, so something interesting from linear algebra is that between a vector space and its dual, there is no natural isomorphism, right? So this is the thing, no natural isomorphism between V and V star. So imagine V is a finite dimensional vector space over some field, right? Dimension of V over some field. For example, real or complex numbers, doesn't matter, less than infinity. There's no natural isomorphism. Although we know that these vector spaces are isomorphic, they have the same dimension. And the only invariant of a vector space, isomorphism invariant, is dimension, right? But there's no, everything you want to write, you have to fix a basis. Or you have to use some extra structure, like a metric or something, raising, lowering indices in that case that you use that. But there is an isomorphism between dV and its double dual, as you know. So V is isomorphic to V double star naturally, without choosing any basis. There's a God-given isomorphism between this and that, naturally. So this Legendre transform is another case where you can construct actually an isomorphism between V and V star from using a function. Okay, so so this is just something to tease your kind of mind about what is going to come. So let f from B to R. This is a smooth function. Be a smooth function. Okay. So if you have a smooth function, then you can take its derivative, df, at any point x. So this is for any x belonging to V. You can take its derivative, this one. I mean, this as an object belongs to V star. It's a covector. It's a linear transformation. It's a linear function, actually. And in fact, the way it is defined is the following: dfx over some vector y in V. It's just the directional derivative of f at x in the direction of y. Right? So this is the limit of f of x plus ty minus f of x divided by t as t goes to 0, right? It's just calculus. Okay, so this guy for any x. Okay, now here is where we assume a condition that I need. So assume that this df, which is from V to V star, is actually a isomorphism. Right? So it's a smooth and with a smooth inverse. Is an isomorphism. Right? So let's assume that this is an isomorphism. Actually, I mean, it need not be a linear isomorphism. We are talking. I mean, isomorphism is not the right word. Not as vector spaces. These are just smooth maps. So I, so let me say I is smooth. Of course, it is a smooth. 1, 1, onto, and then we know that the inverse is also smooth. Right? I mean, a nonlinear isomorphism from R to R. Can you give me a nonlinear isomorphism from R to R? I was going to say something if the f of x is equal to x cubed. This is pretty good, but the inverse, unfortunately, the derivative at 0 is 0. The inverse at 0 is not smooth. So we have to repair that. I can add x to it. So x cubed plus x. How about that? Is that now 1-to-1 also? X cubed plus x, the derivative is x. Yeah, it's increasing. So yeah, so this is so f of x equal to quarter of x4 plus half of x2. It gives me this, and this is an example of a nonlinear isomorphism from R to R. Yeah. Still, I mean, yeah, okay, so the derivative of this is never 0, so that's pretty good, actually. It's 3x2 plus 1, so the non-linear. Okay, anyhow, so we are back to general case. So we look at a function that has this property. Then we can define the Legendre transform. So this is the definition. The Legendre transform of f, L of f, is the map, is the function. LOF, which goes in the reverse direction from V star to V. You may be tempted to take the inverse of this function here, the F. It's almost like that, but not quite. There is some subtle difference defined by so LF. So I denote elements here by P, so for momentum. So this is kind of momentum space, or frequency space. The other one is, yeah. So at P is equal to inner product of P x, right, minus f of x, where x is defined by this x is defined by this equation df of x equal to p. I mean, it's quite a strange definition, right? Because so we just take, I mean, first of all, what does this mean? This is a covector and this is a vector, right? We evaluate this linear functional and this vector. So this is a number. And then we evaluate f at the solution of this equation. That's for each p, because we assume that it's diffeomorphism or isomorphism. For each p, there is an x, so just okay. So this is Legendre transform. Okay. So so this was defined by Legendre in kind of maybe old notation, actually not modern notation, around 70, 80s. Legendre used this to turn nonlinear PDEs to linear PDEs. So it was a huge thing. So nonlinear PDEs to linear PDEs. Then this was used in mechanics to turn actually, you show that, so okay, so I will come to that, but basically Legendre transform of Lagrangian of Lagrangian is equal to Hamiltonian. That's it from classical mechanics. We'll see why that's the case. And this Legendre transform turns Lagrange equations, which is nonlinear ODE, equations of motion. So these are nonlinear ODEs because second order nonlinear ODEs. They are turned into linear Hamilton's equations. Of two variables, double variables. Hamilton's equations. And yeah, so it's quite a big deal there already in these two instances, but it's everywhere. In thermodynamics plays a big role, and in a lot of places. Okay, so let's see why we did this. So, right. Let me give you an example. Any questions? Yeah, so let me now give you an example. So this is example one. So F goes from R to R. F of x equal to 1/2 A x squared. And of course, A is different from C. Right? So let's compute the Laurent transform of F at some covector P. Right? So what is that? That's Px minus f of x, where x satisfies the equation df of x equal to p. Well, this is nothing but 1/2. df is just ax, right? Equal to p, right? So then it follows that x is equal to p over a, right? So x is equal to p over a. And then we just substitute here. So it follows that LF of P is equal to this part. I have to put this here. So I get here just a multiplication of numbers. This is P2 over A minus 1/2 A P2 over A2, right? And if you compute this, you're going to get, 1/2 1 over A P2, right? So again, it's a quadratic function, but the coefficient is transformed into 1 over A. That's an important thing. That's the duality. It's 1 over A. Of course, you have seen this business of 1 over A before, right? In Gaussian integrals, when we calculated this, also it was again a Gaussian with 1 over the A, or 1 over matrix, inverse matrix. Okay, so here's second example for you to feel more comfortable. So, this is an exercise. I want you to show that if f of x is equal to x to the alpha over alpha, where alpha is bigger than 1, a function like this, where from R to R, then using this thing, you can show that LF, the Laurent transform of F on X is equal to x to the beta over beta. But beta is the unique number that satisfies the equation 1 over alpha plus 1 over beta equal to. And this is kind of like a functional analysis duality between LP and LQ space. Yeah. Okay. So we have that. Right. And so I can give you a kind of more relevant higher dimensional example. This is the quadratic part. So this is example 3. So let's assume you have a quadratic function f from Rn to R, f of x is equal to 1/2 bxx is equal to 1/2 in matrix form bx as we always wrote them in 2 forms, right? So imagine you have such a thing, and this p is non-degenerate. The different from 0 and b is symmetric. Okay. Then you can show easily here that f of t is equal to 1/2. In fact, this exactly gives us P inverse P and P. Yeah. I mean, I can even write it in a third form, which would be something like 1/2 sigma P I J X I X J I J from 1 to n. It's a quadratic function. And if you take its derivative and then you get this matrix B and then you invert it. So example 4, this is in classical mechanics. I don't need it, but I alluded to classical mechanics. So, I mean, this Lagrangian, I mean, you call it L, it is a function of two variables Q and Q dot, right? So we can think of it as a function of the tangent bundle to R, from Tm to R. This is a tangent bundle thing. So we apply fiber-wise Lausanne transform. Fiber. So we apply to fibers only. We don't apply to the X coordinate, to the Q coordinate, only to the Q dot coordinate, fibers, tangent direction. Fiber-wise Lausanne transform. So what we do in this case, so L of L is a function then from the dual space to yeah, R, and this so I mean typical case here L. So allow me to write it in terms of QQ dot coordinate, which is for mathematicians is a nightmare to understand that, but by this now you know what we mean by this notation. So 1/2 m norm of q squared, q dot squared actually. The velocity, this is kinetic energy minus potential energy, minus V of q. Minus V of q. Right. Now, if you do this, L of you do the Lausanne transform of this type of Lagrangian, which is kinetic minus potential, right? Kinetic minus, and this is a metric, Riemannian metric on the manifold, for example, can be changing point to point even. That's okay. So this is the given by the Lausanne transform of this Lagrangian on Q and P is basically equal to norm of P squared over 2m. It comes down, this m, as we saw in first example, plus V of Q. So this is kinetic energy was written in momentum term and then potential. So this is kinetic plus potential. This is kinetic minus potential, which is not Lagrangian. K minus V. Okay, yeah. Yeah, so that's the there is one crucial property. I don't need it now, I think, but one crucial property of Lausanne transform, which is it's exactly a duality. Namely, if you take the Lausanne and then take Lausanne again, you're going to get the original function. That's really amazing. So I really want you to think about this exercise. L2 of f is equal to f. Right? Because so to do that, we have to identify V with V double star in the natural way. Because you see, L of F goes from V star to R, and L2 of F then goes from V star star to R, but this is naturally isomorphic to V, so there's nothing, there's no danger in writing this equation. This is coordinate independent. This is the duality sense of histogram transform. So it's really amazing. Yeah. Good to think about. Okay, so before we finish, still have time, but that's I want to get now. Okay, so let's first this. All right. Yeah, so with this understanding now, it should be easy to grasp what I'm writing now. Okay. Any questions? Yeah. Yeah. Okay, so back to effective actions. Okay, so right now let S of x as usual is quadratic part. And then some cubic terms are extra. So it means that the next terms are cubic and higher orders as they go, right? So now let z of j, now we're going to introduce this generating function. So this generating function, z of j, we didn't work much with it except for the first lecture, but it's absolutely essential for QFT. Z of j, which is partition function to the source. Function with the source. So this, by definition, is defined as h bar to the power of negative b over 2 integral rd exponential of minus 1 over h bar s of b s of x, sorry, minus j of x, right? Okay. Well, I mean, why is it called generating function? It is a generating function indeed, because if you differentiate this with respect to j many, many times, you're going to bring these x's down here, and then you create all correlations, basically. So this is really a generating function for correlations. And log of this is usually denoted by wj, which is connected generating function. So this is log of z of j. Yeah, but right. Okay. Now, so what we're going to do now is we are going to apply this definition of effective action, but with the source added. Okay. So now log of z of j over Z0, right? This one is equal to negative S effective of X0 and J. So before we had this equation without J, and that's a more or less definition of effective action, because when you calculate this summing over 3 components of the effective action. So where X0 is a solution of delta S of it's effective, right? X0 equal to Z. This is the equations of motion with this parameter J. And as effective was defined in a previous theorem that I didn't prove, but I get to the proof, but was defined in a previous theorem. Okay. But then something very interesting happens, namely, adding this linear term actually does not change the effective action if you add linear term over there. So let me write it, but from this definition follows that actually, the effective action with respect of X and J is effective of this action now of Xj here, Xj is like calculating the original effective action and then adding simply the linear term here. So look at this equation. I mean, this is exactly the definition of Legendre transform. Because we have, look, we are interested in minus S effective Xj. And that's really Jx minus S effective X. And this is really the definition of Legendre transform. So it follows that almost like or nothing thus, let me write it again, log of or ln, I've been writing ln today, ln of Zj over Z0 is the critical value of Jx minus S. So we can write that indeed as effective, that's what we wanted, of X is actually Legendre transform of log of this partition function, generating function, partition function, Zj over Z0. And by the Legendre duality, that L2 equal to identity, same thing, you can just take 1 of this guy, Zj over Z0. Is equal to Legendre transform of the left-hand side by duality that I know. I did not prove that L2 equal to identity, but I gave it as an exercise. Equal to L of S effective of X. So I mean, so this is Ettinghoff put it this way, which is very nice. He says that this is say effective action, is equal to Legendre transform of the generating function for correlation, namely Z of J for correlation. Z of J. Well, I mean, there is this factor of normalization, Z0, and vice versa. Yeah. Right. So, I mean, again, it looks like we haven't done much. It's almost like a tautology at this stage. But the power comes from the fact that S of F is indeed allows a perturbative expansion in H bar, starting with the original action S, and then there is S1 H bar. See, here is S effective is equal to S plus H1 of H power 1 plus H power 2 S2, so on. And this part, using this theorem, can be computed by solving equations of motion and really finding roots of equations. So this is quite. So I'll give you an example later how this is done in action. Action is done in action, right? So yeah, I mean. Okay, so I have to prove that theorem still, and then. And I have to give an example of this, which will come next. Are there any questions? Okay. So basically, so one of the things that I didn't do in this part was the Laplace method and also the stationary phase approximations. I was eager to get to this part, which is kind of, I don't know, more eye-catching to do this and has applications. But those two results are like horseworks, working courses for us, more or less. So we need to have them completely under our belts so that we can use them in time. So yeah, so I'm going to discuss that now. So we're going back in terms of Ettinghoff notes, we're going back to the earlier sections, which I dropped in order to get to this, because I didn't need that thing. Now we're going back to, okay. So let me motivate this. in this way. So the discussion is centered around the idea of asymptotic expansion. So I want to discuss at least two topics, which is Laplace method. And the second one is stationary phase approximation. Phase approximation. Okay, so what is the story here? We saw that formally, I mean, this was Feynman's theorem. Any integral like RD exponential of minus 1 over h bar s of x dx, whether it is convergent or divergent doesn't matter. We can make sense of each term, which is finite, write it as a series, and this is basically equal to sum over some terms, which is over graphs. And this is the equality of formal power series. Formal, and this is a perfectly mathematical theorem, and that's what formal power series. Right? I mean, just to give you context, I mean, r exponential minus 1/2 like x squared plus g x cubed, for example, dx. I mean, for any value of g except g equal to 0, this is divergent. You cannot make sense of it. But as a formal power series, we know how to make sense of it. And we know how to write it as sum over graphs. And that's the theorem. But assume that actually this guy is convergent somewhere, because it can converge somewhere, right? I mean, for example, like this. For G negative, this is convergent, right? G negative, convergent. Right? If G is negative, this is convergent. So the question is, what happens? What is the relation between summing over graphs and this convergent? That's a question, important question. So we want to know now, what if the integral is convergent for some values of coupling constants. Is there a class here? I don't think so. No, we have it till 3:30 for sure. Of coupling constants. I mean, e.g., in this example, e.g. as in stop. This is stop. So we discussed this before, but let me write it. Let me say it again. We may hope that, okay, this is convergent, and this is a power series, and this would be actually equal to that. But that's hope in vain. This is never convergent. It's always divergent, the power series, because we estimate the coefficients, and the coefficients always grow factorially. So they're always divergent, even for finite dimensional integrals, right? But the right-hand side, sum over graphs, is always divergent. I mean, for any g's, except different from 0. Of course, for g equal to 0, you're back to Gaussian, and that's not the problem. But yeah, it's always divergent. I mean, the coefficients grow factorially. So it looks like that, I mean, the usual idea of summation is completely useless here in terms of summation of series in the usual sense. But this is always divergent, this is convergent, there can't be relation between the two. But there is a relation, and the relation is that actually this thing is asymptotic expansion of this one. But there is a relation in terms of not summing a series, but summing as an asymptotic expansion in terms of asymptotic expansions. So let me write the result, which is called Laplace method. So here's the theorem. This is called Laplace method. So we get the coefficients completely honestly. Okay, so yeah. Yeah. So you can formulate it in different forms, but here is one version. Assume F has a global minimum in C belonging to open interval AB, such that it's actually non-degenerate minimum. So the second derivative is positive. That's what we torture our calculus students with these questions. Positive. Then integral from A to B exponential of minus 1 over h bar f of x dx is equal to root h bar exponential of minus f of c over h bar times I of h bar, where this I of h bar where I from 0 infinity to r is smooth. That's important. It's smooth. And I of 0, we know its value as 0. So if you take 0 here, you're going to get root 2 pi over f double prime. That's 0. And you can see this is a Gaussian contribution of the second derivative, Gaussian part. Yeah. And I of h bar, it's very interesting. And this I of h bar, this function that gives us the expansion, only depends on germ of the function around C. It's independent of the values of function at points which are just even an epsilon away from C. It only depends on the infinitesimal neighborhood of C. So there's a mathematical term for that because I of h bar only depends on germ of C. Actually, it's even, I believe it's even less than that. So let me tell you on germ of F at C. So basically, this means only on the value of the function and its derivatives and higher order derivatives at C. Actually, that's what matters. These values, the derivative of function at this critical point, that's all matters. So if you can see the function around critical point, if you can compute all the derivatives, then you have complete information about this. Right. So let's look at this. This is really an equality. This is an equality. This function, I mean, this is for h positive, but I mean, even on 0, I would say even negative. That's what people positive, let's say here. So this function I of h bar is smooth, but it's never analytic. It's never analytic. So what happens is the following. Let me tell you what happens here. Then, okay, so before doing that, let me say this. Then we use Taylor's theorem. Then applying Taylor's theorem to I, Taylor's theorem from calculus. And then we can say that actually the value of the integral exponential of, minus 1 over h bar f of x dx minus, take as many terms on the right hand side as you wish, root h bar exponential of minus f of c over h bar times 1 plus, so f of 0, times a0 plus a1 h bar plus a2 h bar squared plus an h bar to the power n. This is equal to O of h bar to the power n plus 1 as h bar goes to 0. Oh, this absolute value. Okay. So what does this mean? It means that this guy is bounded, the difference between this term, which is, on that one, is as h bar goes to 0, is already bounded in h bar of order n plus 1. So this is less than equal to some m times, this means less than equal to some constant m times the absolute value of h bar to the power n plus 1. And you notice that, so this is a great kind of approximation to this, because as h bar goes to 0, this quantity is 0 of order n plus 1. So that's a very good approximation. But that's not the approximation in the sense of power series. In the sense of power series, what you do, you just let n goes to infinity, and h bar is fixed. That's not true. That's the dual one. So that's asymptotic expansion. You see? So there is a relation, kind of asymptotic expansion. I mean, this concept is much more subtle, asymptotic expansion, usual compared to usual power series expansion, usual summation of series, because that's why it was the definition came quite late. Actually, it was done by Khalkhali. 1880s. Khalkhali really wanted to understand what these astronomers are doing, because they were writing all these series and they were using it to approximate the orbits of planets. All series are divergent. How do you use divergent series to approximate? For example, using a Stirling's formula, it was noticed actually by mathematicians that the Stirling series is divergent. And there was one mathematician, John Bayes, he was a reverend, actually, British reverend, late in 18th century. He wrote an article about this. He said that this series, a Stirling series, is divergent. I think it's not very easy to prove, actually, but he was convinced it's divergent. And so he said that anything that is based on this Stirling series is wrong. Which actually is quite correct. Because, I mean, it's really interesting thing to see how, you know, we can be brainwashed by some ideology like this. Power series is everything. Oh, I mean. So anyhow, so this came quite late, actually, the idea of asymptotic expansion. So I think it's a good time to stop, and because the next topic is I want to use this Laplace method to prove to drive the Stirling series as a nice example. And then we go to a stationary phase approximation, which is the complex version of this, oscillatory version. That's a bit more subtle. By the way, there is an n-dimensional version of this. Obviously, you can see that, for example, in this case, it's going to be the Hessian matrix of the thing, and it's going to be D instead of 1/2, it's going to be D over 2 power here. I will write it down. Another thing is A to B, what we are dealing with minus infinity to infinity. What about that? It doesn't matter. If your function is such that this is convergent, then away from the critical point, the contributions are infinitely small. So they don't matter. Another thing is that actually this asymptotic expansion, it will never give us the actual value of the function. Almost never. Yeah, because, I mean, it's not unique, I'm saying. If you add some term like e to the minus 1/h2, this guy has all its derivatives 0 at 0. So if you add it to some function f, I mean, they have the same asymptotic expansions. So you cannot go back from asymptotic expansion to the function. But from Taylor series, if it is convergent, you can, right? Because Taylor series is really the value of the function, but this is not. So yeah, you have to go a little slower there. And the proof of this Laplace method, you can find it in Ethical. It's a kind of mess. It pains me to go through it, so I try to avoid it. Yeah, it's the most important thing is to be able to use it. I mean, I understand. Okay, I think, are there any questions? I think we are good now.